Morning with Martin.
And
by the way, I was reminded by a group of people yesterday that one should not bring drinks inside this class. So thanks for your cooperation.
Okay, thank you very much. So I will be talking about weak lensing peak counts. And this is some work I've been doing with my former student, Tia-Ann Lin, who is moving to Edinburgh, and people in my own lab, Sandrine Pires and Austin Peel, who's also giving a talk later. Okay, so I hope you went to the weak lensing lectures 2 weeks ago. If not, I'm very sorry. I just have one slide for you on lensing. But I think you all know that cosmologists like weak lensing because we probe the baryonic and the dark matter at the same time. So we don't need to assume any relationship between the two. The galaxy bias is a difficult thing if you do a galaxy clustering survey. And we kind of probe the epoch of accelerated expansion. And because weak lensing is sensitive to both the geometry and the growth of structure, it's an interesting probe for modified gravity. Okay, so we go to really small scales of the large-scale structure where we know the properties are non-Gaussian. However, up to now, most of the observational results have been obtained by just second-order statistics, like the power spectrum or the correlation function. Right? So, for example, you take like your projected overdensity, and you take like the variance in circular areas to get like the variance of your structure, and this can be related to the shear field, so the distortions that are induced to the galaxies by weak lensing. So that's kind of what we can observe. And you can get the variance here, they have a correspondence, or you just calculate a 2-point function between your fields. And this gives you a handle on the power spectrum, so the Gaussian statistics, right? But we want to go beyond that to get the features of the non-Gaussianity. So one way would be the bispectrum or the 3-point function, and then you just correlate 3 points in your field, so the projected overdensity or the shear field, or you just take the third moment of your density field. There are other ways like the Minkowski functionals, but in this talk I will mainly focus on peaks, on peak counts. Okay, and one other interesting thing about these higher order statistics is if you combine them with second order moments or second order statistics, you can also lift parameter degeneracies, because second and third order moments of the large scale structure have a different dependency on cosmological parameters. Right, so for example, if you look at this plot of omega matter and the power spectrum normalization, these are all predictions or simulations here, you get slightly different dependencies between the second and the third moment, or here, of the convergence field. So if you combine the two, you get tighter constraints, ideally. Okay, so we did measure higher order statistics in the CFHTlens survey a couple of years ago. So here in this plot, you see the third moment of your shear field, basically. And the data points is this E-mode correlation, basically, of the third moments as a function of angular scales. So you can see it's in good agreement with WMAP9 at the time and the clone simulations. These are n-body simulations. But if you look on this right-hand side, you see the B modes, right? So if you take your shear field and you project out those kind of electric field modes, this is just like CMB polarization. So these are the modes that are created by the large-scale structure in a physical way. But these B modes should vanish. And we know this is leakage on small scales due to the discreteness of your galaxy field, of your galaxy distribution. But even on larger scales, where there shouldn't be any B mode, there is actually a B mode. It's difficult to see because the points are much smaller than the E mode, but they are still significant because the error bars are fairly small. So we do have this problem. And if the presence of B modes usually is seen as a sign of residual systematics in your data, like the data reduction didn't work that well, the PSF correction, for example. But there are more problems on higher order statistics. For example, the prediction you need to model this observation, if you want to get cosmological parameters, they are only accurate to maybe 30% on these small scales where we measure the weak lensing signal, like arc minutes or 10 arc minute scale. Right? So for example, the bispectrum is a function of the power spectrum typically. So you need a model for the power spectrum, and these are the different curves. So this is like the original halo fit, the Takahashi halo fit, or the Heitman Coyote simulations. And then this function f is also, you can use prescriptions from n-body simulations. So you see, you get quite different answers. I mean, they're still compatible with the data with these error bars. But this was a fairly small survey. And you know, for larger surveys like Euclid, we cannot tolerate this anymore. And then if you look at the distribution of your observable, this is plotted on the right. So these are the third order moments at 2 different scales, like 3 arc minutes here and 30 arc minutes on the right. And from n-body simulations, we get a histogram, we get a distribution of these moments. So you see they're skewed, right? It's clearly visible if you don't have noise. If you add noise, well, it gets more Gaussian, but still you see a strange distribution. So we don't want to model these observables as Gaussian, right? It's clear because they're non-Gaussian observables. But usually we just take a Gaussian likelihood function to make things simple. So it's more complicated for these higher order statistics. Okay, so that's kind of what I said for the third order statistics. They're interesting because they do capture the non-Gaussianity, and in a way maybe less than expected, they do lift parameter degeneracies. But as you could see, they are prone to some residual systematics in the data. I haven't talked about astrophysical systematics, but they're also usually higher for third order than for second order statistics. And I showed you the problems with the model and the non-Gaussian likelihood. But we have peak counts, and hopefully I can convince you in the next few slides that this is also a non-Gaussian probe. In a also limited way, it can lift parameter degeneracies, and there's some it's not quite clear from the papers that have been published so far. But it's less prone to systematics in the data. We maybe can deal with the model uncertainties, and we definitely can exploit the fact that you have a non-Gaussian probability function. Okay, so what are these peak counts? Well, you just take your overdensity field that you can get from lensing, so your projected density field, and you count the maxima, right? So this is clearly a non-Gaussian probe because it's the high density regions in your field. And I won't go much into detail, but you can do this basically in a linear way from your shear field. So you don't have to calculate complicated third-order correlations, and you get kind of correlations with the systematics of the data. But you can do it in a linear way, and you also can do it in a circular average way. So a lot of these large mode systematics cancel out, and this has been actually seen. So it's less sensitive to systematics. And well, these high-density regions in projection, they are a tracer of the mass function, of the halo mass function, right? Because it's believed that a large protected overdensity in the lensing signal corresponds to a halo, right, to a massive halo. And that's why it's also interesting for modified gravity, because you get modifications of the mass function at the high end, typically. But it's a fairly indirect probe, I have to say. First, you have noise in your data, so the fact that the galaxies are not round. So for a given galaxy, you don't measure directly the distortion from the shear, but it also has this intrinsic component, which is much larger than the shear. So this noise can actually change by quite much these maxima. And you get an asymmetric effect, so you get more upscatter if you think about signal to noise than downscatter. It can create false positives, so maybe this is actually not a halo, but just some random fluke signal. And also you get projections along the line of sight. So any of these points need not be a single halo, but it could be several smaller halos in projection. So it's difficult to model this. This part is easy, so the counting, right, from this map, you can just make a histogram, for example, as a function of signal to noise of these detections. And then we have to go back if you want to interpret it in terms of cosmological parameters. So if you want to have this observation and then infer sigma 8, let's say. Okay, so what about the models? Well, there have been attempts for analytical models based on Gaussian random field theory. They're not bad, but clearly they're limited because, well, you need some add-ons for the high-end tail, which is non-Gaussian. And it's difficult to add systematics in these kind of models. And it's easier to do with the forward modeling. For example, you take an n-body simulations, you run different models, and you try to predict the number of peaks you get. Here it's straightforward to include systematics, right? For example, you can just add errors of your redshift to each of the galaxies, or you can add intrinsic alignment and so on. However, if you run an n-body simulations, well, obviously it takes a long time. you're probably limited to a few parameters that you want to explore. And you need both large boxes, because high signal-to-noise peaks are rare events. You don't see them that often. And you also need a good resolution to resolve like the small scales that we can probe with lensing. And that's why my student and I tried to come up with a new model. And I'm going to describe this model here on this one slide. So if we're only interested in counting the high-density regions, we're not interested really in the correlations or the spatial distributions. Our idea is just to get rid of an n-body simulation and just to replace this basically by random samples from the halo function, and then putting these sampled halos, these simulated halos, in a kind of Poisson way along the line of sight. Right, so there's no clustering. In terms of the halo model, what we're doing is we simulate the one halo term. So we don't have the two halo correlations. And then we compute the lensing signal by just doing some ray shooting. We add noise. We create these filtered maps. And then we can predict the number of peaks we have. Okay. So we're making two major hypotheses with this model. First is that, as I said, the clustering is not present in our model. So we assume that clustering of halos is not important for the number of peaks. And this has been shown to be fairly true along the line of sight by this paper by Laura Marian. And the other hypothesis is that unbound large-scale structure does not contribute to the weak lensing peaks, because we're only simulating halos. So we don't have like diffuse structure. So, but this is also true for the halo model, if you do a halo model approach for the power spectrum. Yes, please.
I think I missed the first point. So why the clustering is not important?
Well, so the hypothesis is that if you just shuffle around the halos, on average, you get the same number of counts, of peak counts. Right? You might reduce some of the halos because of projection effects, but then you may be adding some signal here. So on average, it should be the same.
So there can you combine effects for a few halos together? More amplification?
So yeah, we do still have projection effects. What we don't have is, for example, like correlated structures like filaments, for example. If you have a filament and this creates a halo peak, then we don't have this in our model. But so our hypothesis is that these filaments are fairly low mass and don't contribute much. And so we tested these hypotheses, and I mean, they're not perfect, as you can imagine, right? So especially at high signal-to-noise, 6 or 7, you do get some differences, and we managed to kind of test these hypotheses independently and then compare it to an n-body simulation. So that's the number of peaks that we get, the peak count density. But on smaller as a signal-to-noise, it works fairly well. And you also have to imagine that the n-body simulation is also just one realization. So it also, in principle, has error bars.
And the halo mass function is taken from the same simulation?
Excuse me?
The halo mass function.
So we had,
from the same simulation or
so the green and the red points is the same halo mass function. So we basically extract the halos from the simulation. And then if you go to an analytical mass function like Schatz and Torman, we get the difference between red and these points. Yeah, so here it's also the fact that the n-body simulation does not follow exactly the mass function. Okay.
So if you do the shuffling, don't you change the redshift of halos, the lensing halos?
So we only shuffle along the same redshift and constant in redshift. So we sample from the mass function for each redshift slice, and then take the mass function as a function of z and mass. Yeah. Okay. All right. So our model is fairly fast because it's not an n-body simulation. It's forward modeling, so we can fairly easy include systematics. And then I'm going to emphasize on this last point because the model is stochastic, right? You sample from a mass function, then you have this random distribution, so it's kind of this random process. And so in principle, if you create a model, you kind of draw this model from a distribution of your models. And this is an interesting point, which is not the case, for some analytical model, because you always get the same model prediction. But here, if we redraw our model, if we rerun our simulation, we get a different answer. Okay, and so before talking about how we can exploit this with this technique ABC, Approximate Bayesian Computation, this is just one slide on Bayesian parameter inference. Right, so what we do, if you have some data and we want to determine cosmological parameters, Well, in the Bayesian way, you're interested in the posterior, so the probability of a given parameter, like omega m, given the data and a model, like lambda CDM. And then you can see it depends on the prior of the parameters. The evidence is not very important here. And the major ingredient is the likelihood function. That's the probability of the data given the model and the parameters. And in general, we need to calculate integrals over this posterior function, right? For example, for the parameter mean, like what is my mean omega m from my survey, I just have to integrate over the posterior times pi times omega m. And these are usually high-dimensional integrals. It's just the number of cosmological parameters you want to probe. Or for a confident, credible region, you just need to integrate over the largest 68% of your density. So in order to do these integrals, people usually do sampling, like Monte Carlo, Markov chain, or some other methods. And then ABC is just another method. Okay. Now, okay, I said this likelihood function is the major ingredient. And so you have to assume a model for this. For example, a Gaussian or a log normal. Right? So it's log normal or the Gaussian in the observables X. So for these peak counts from recleansing, we assume the Gaussian likelihood function in this plot. And then we can also vary kind of the which parts of this function depend on parameters. So for example, we can have a covariance that's constant or a covariance that's varying. And then we get these kind of contours. So this is all from simulations. Right, so these are the credible contours for omega matter and sigma 8. You get this typical banana shape from recleansing. And then you get differences, if you take the covariance constant or varying. You get this difference between the colors and these contours. Okay. So this is just an example of what people usually do when they assume a model for this likelihood function. This is another plot what we do. So, okay, the likelihood function tells you how likely it is that a model that you create, given a parameter pi, is in accordance with the data, reproduces the data. Right, so in a classical way, you answer this question by assuming a model, as I said, like a Gaussian, at a screen curve, for example. So it's a Gaussian, and then you plug in your data, and you calculate this function L. So let's say this is your model, likelihood function. Here's your data, so you would calculate this point here, this value. So you see it's not a very high likelihood, because in this case, the likelihood function would prefer data that's more over here, right? So this is maybe with a model parameter that's not really in accordance with the data. But you see, maybe the Gaussian approximation is actually not very good if the true likelihood is different. So an alternative way would be this on the right side. So imagine someone gave you realizations of your model predictions, like in a stochastic way, which are drawn from the likelihood function. Right? For example, if you run many n-body simulations, and for each simulation you predict what your observable is, like your power spectrum or your peak counts, these points would be drawn from underlying distribution. Right? And the density of these points are then proportional to the likelihood function, to this distribution. So these points kind of sample the density. And then what you do is you have to evaluate this kind of likelihood function at the position of your data. Or you just, for example, if you have discrete data, you just ask yourself, how many times does my model reproduce the data? Or if for continuous data, you have to take some kind of small tolerance region and ask, how many of these data points fall into the small region? And that's also the likelihood of your model to reproduce the data. Okay, that's another slide saying basically the same thing. So the density of these sampled points, if they're sampled under this likelihood function, the density is then proportional to this likelihood. And then this probability is nearly like in a frequentist sense. You just count the number of models that are close to your data and normalize by the total amount. And in this approximate Bayesian computation, there's now this magic ingredient in that you actually, for a given model, you don't have to sample n equals 100 times. It's sufficient to sample one time. Right? So you just sample one point, and you reject this point if it's far away from your data. You accept it if it reproduces your data. And this works because at the end, you're going to sample a lot of points in parameter space from many values of, let's say, omega matter and sigma 8. So here you create, of course, a large uncertainty, a large noise, like sampling noise, but you overcome this noise by just sampling a lot of points here in this space. Because this process is done just for one model prediction, for one model. Okay, so this is basically approximate Bayesian computation. So you can see it can be done if it's possible and easy and fast to sample points under this likelihood function. So it's probably not feasible if you have to run an n-body simulation for each of these points. But with our model, it's possible because it's fast. And so this is useful if you're not happy with the situation that the Gaussian function is a bad approximation of your underlying likelihood function. And so again, in the simulating process, you sample from this function without having to know this function. You don't have to assume anything for L. This kind of comes naturally to you. Okay. Or it could also be that the evaluation of this likelihood function is very time-consuming, very expensive. Or if, in any case, your model is intrinsically stochastic, then you can also use this. Okay. So I try to come up maybe with a more intuitive way how to explain this, and well, I didn't succeed, so I watched some TV, and I saw David Spergel making soup. Okay, great, that's a great example. So imagine David is making soup, and you're getting the final product, and you want to determine what were the ingredients that went into the soup, right? So you can try to model this process. It's super complicated because you have to know when these different vegetables boil and how they disintegrate and so on. So that's way too complicated. But instead, we just asked David to make lots and lots of soups with different ingredients, and then just compare our soup that we have with any of these models. Right? And this works if this is a representative coverage of your ingredients. Okay. And actually, we have now the main ingredients for approximate Bayesian computation here. So we have to first know what aspect of the data do we actually use to compare to the simulation. Right? Do we, like in the soup case, do we use the smell or the taste or, I don't know, whatever, the consistency? And that's in ABC, it's called a summary statistic. But this you have to decide anyway, even if you do a classical likelihood analysis. Right? If you have your CMB map or your weak lensing map, you have to know what aspects you use. Do you calculate the power spectrum and then simulate it, or the bispectrum, and so on. Then you have to get a metric how you compare your data in your simulations. And you can also freely choose this metric or this distance. So this basically then tells you how you can tell whether some model is close to your data or not. So it's a metric, right? And then for this accept-reject algorithm, we have to decide a tolerance, a small interval around your data, when to accept this. Okay, so now let's go to a more cosmological example. So this is again for weak lensing peak counts. So as a summary statistics, we just take what I call X. So it's basically this histogram that I showed earlier. So the number of peaks you get as a function of signal to noise. So the PDF basically. And you can do other things. And the metric in these two cases between, let's say, your model and your observation, in one case it's just basically the weighted kind of chi-square distance. And here I use the full covariance matrix between. So this accounts for the correlations between the data. And we use these two in two different data. But I want to emphasize that even if you do this distance without taking into account the correlations between data, this is only the distance, right? This is only when you tell whether the model is close to the data. The correlations between the data points, I think, are taken into account by your model already, because it draws from this joint distribution of, if you have a d-dimensional data set, it draws from this d-dimensional distribution with the correlations in it. Okay, and then we have this algorithm. It's an iterative algorithm, and then I'll just show this movie if it works. Right, so for omega meta and sigma 8, you see these iterations. So at the beginning, we just draw points from the prior, so they are uniformly distributed. And then, kind of similar in an MCMC, you propose a new point, and you check this distance, and you see whether it's below the tolerance or not, and then you keep or reject this point. And again, I have to emphasize that this distance is not calculated here in this parameter space of omega m and sigma 8, but in the space of observables, so in the space of your histogram counts. So it works quite well. And we have like a stopping criterion. I won't go much into the detail. But you can also imagine that once you're at a certain point, so you're already fairly well sampling your posterior, the efficiency gets down, because a lot of new points that you propose will be too far away from your data, right? So they will be rejected. So each of these iterations take more and more time to run. Okay, here's a comparison of ABC with the Gaussian likelihood function. So the Gaussian is in orange and blue, and the ABC posterior is here in the dashed lines. So they're slightly different, but actually if you look at the points, so these are the final points that are accepted in my ABC PMC algorithm, and they have different weights. But the weights are not taken into account in creating these contours. So you can see in the point distribution, you do see this banana-shaped bending more than you do see here. So I think this is a smoothing effect, that the fact that it's not entirely overlapping. And also, I guess you don't expect that. I mean, the whole point of this work was to probe a case where the likelihood function is probably not Gaussian. So you do expect some deviations. Okay, I will skip this slide. Right, so I haven't talked about modified gravity at all yet. So I have a few slides. So now with this model, we tried to see what kind of constraints we could get on f of r. Right? So we took a mass function from Patrick and his student Luca Rizzo, and we just inserted this new mass function into our model and predicted the number of peaks as a function of signal to noise. So we have like lambda CDM here in magenta, and then these different f of r models with increasing R0, R0, 10 to the minus 6, 10 to the minus 5, 10 to the minus 4. So you do get a difference, but mainly on the high end part, right? Where we probe the massive halos. But you also have to make sure you really know your mass function well for the standard cosmology, because if we change from, I think, Sheth and Torman to Jenkins, we also get a difference that's comparable to these different f of r models. So I think we have to be careful. And the error bars correspond to about 3,000 square degree survey. And there was this paper by Vincenzo Cardone a few years ago, who also took an f of r model, and he parameterized it with this epsilon parameter, which is more or less like the log f of r naught. And you can kind of see the constraints from, or a Euclid-like survey. So I think these constraints are much better because it's a larger survey, and he used the fact that galaxies are at different redshifts, whereas we just took all the galaxies in one redshift bin, basically. So we don't have the information along that. We just project them out. And here he uses the redshift information in a better way. And then, this is a measurement from last year from the CFHTlens survey. So the survey I've been showing before. I guess you can't see the plots very well. So this is from simulation. This shows again the difference of the number of peaks normalized to GR for f 10 to the minus 4 and 10 to the minus 5 of f of r. So again, you see most differences on large signal to noise, where you have the massive halos. And so this is the observed peak counts. I think these two curves are WMAP and Planck predictions. So you see a different normalization. And then they obtain contours for sigma 8, omega m as a function of log fr naught. So they can they say they can exclude very large values of this fr naught. Okay. And this is another plot from our paper, where we included now also the dark energy parameter of state. So again, we don't use the redshift information, and I think neither did they. So I mean, they determined the redshift distribution of the whole population, but just in one redshift bin. And we did the same. So you can see that the constraints on W0 are not that great. So you really need to add these redshift tomography to get improved constraints. Okay, I think I'm probably running out of time, but that's my last slide. So I talked about recleansing peak counts. I hope I could show that it's an interesting probe for non-Gaussianity of the large-scale structure. And you could, in principle, get information on f of r and dark energy. And then I spent a lot of time on this ABC. And it's getting, so I think it's a fairly new method in cosmology, but it's getting more and more popular. So this is a list of non-exhaustive list of papers. So people used it to model galaxy morphology, supernovae, galaxy cluster counts, image simulations, and so on. There's our paper. Yeah, so a lot of these cases, you can see you don't need to really model the large-scale structure, because that's a difficult thing. There you'd really need an n-body simulation. But like to model supernova, to create these stochastic models, it's easier. Or for galaxy cluster counts, it's similar to weak-lensing peak counts, HOD models. So I think it's a promising approach in some areas, but it's limited at the moment to the speed where you can create these simulations. And I think I'm going to end here. Thank you.
Thanks. How much do like baryonic physics change the peak counts?
I think there are, I know about 2 papers who are kind of contradictory. So one paper says it changes peaks more than Minkowski functionals for power spectrum moments. And I think another paper said that it changes not that much. So I think the jury is still out. I guess it depends on the smoothing scale. If you maybe, because I haven't talked about filtering your data yet, but you have to filter your map with a smoothing scale. If you go to large smoothing scales, I think baryonic effect gets smaller, but also your power to constrain parameters gets smaller.
In relation to that question, you checked the effect of varying the halo concentration on the peak counts.
We did, yeah. I remember more another paper, not by our group, by the paper by the group of Fan et al. They also included the concentration on, actually they tried to measure the concentration from data, and it does have an effect, yeah. So, okay, now I remember, yeah, we changed the concentration, and it has quite some effect, yeah. It changes the number of peaks you get. Or the CM relation, yeah. It's sensitive to that, definitely.
So regarding the f of r, yeah, just that slide, that one, so you say the models you are testing is f of r 10 to minus 5 and 10 to minus 4.
Yeah, that's 10 to minus 4, 10 to minus 5.
But those models are kind of ruled out, is that correct?
With other data, but that's
my question is, if you are careful with the solar system and with all the other constraints, can you still use this technique to constrain f of r?
I mean, you can see it's not very sensitive, right? So if you believe that 10 to the minus 5 is already ruled out, this result does not add anything. So it's more like a proof of concept, maybe. So it gets interesting if you can rule out maybe 10 to the minus 6, I guess. So you would have to get a much larger survey. And yeah, so at this point, yeah, I don't think that this is competitive with solar system constraints. That's true.
But the solar system constraint depends on whether the galaxy is screened or not, right? So it could be that F6 can still pass solar system constraint.
10 to the minus 6? Okay. I don't know. I'm not an expert on that.
So if you take these f of r models and the equivalent, conformal equivalent transform dark energy model, will you find any difference, any distinguishable effect?
Distinguish between dark energy and modified gravity?
Yeah, for these particular f of r models.
That's a good question. I don't know. I don't think people have like compared the 2 models. Yeah, I can't.
I don't think you should find any difference. But okay.